Welcome to the demonstration of the trigger-based vision system implemented with eInfochip's iCRE QRB4210 platform. The trigger-based vision system is required to detect specific events or conditions and automatically perform an appropriate action. On such a system, the action needs to be taken as quickly as possible after trigger is detected. In this exercise, we have targeted less than 1 second of latency between trigger event and first frame available from camera. The iCRE QRP4210 platform operates on an open embedded based Linux distribution. To ensure swift reaction to external triggers, we have targeted two approaches, which are boot time optimization and device low power mode. Now let's look at both approaches one by one. First approach, boot time optimization. Boot time optimization is the process of reducing the time it takes to cold boot a system and become fully operational. To achieve this, we modified the Linux kernel, removed unnecessary services, disabled unused interfaces, and eliminated redundant init processes, ultimately reducing the boot up time from around 40 seconds to just 8 seconds. Due to multi-stage booting, which includes multiple components, the device could not boot up within 1 second or less. Due to this limitation, we switched to device low power approach. Second approach, device low power. Unlike the cold boot approach, the device remains in low power mode and resumes from low power mode when an event is triggered. Resuming a device from sleep state is considerably faster than booting up a device from cold boot state. During the demonstration, the first frame from the camera sensor was received on the DDR in approximately 400 to 500 milliseconds after the trigger event occurred. While the device does not consume any current during the power off state, it consumes around 7 mA of current during the low power mode. In this demonstration, the RTC wake alarm was used to generate the external trigger event. The latency is measured between point A and point B shown here, where point A represents the moment the application processor receives the external trigger interrupt, and point B represents when the first frame becomes available in the DDR. A script is used to automate the test setup and derive average latency by performing multiple iterations. Flow of the script is visible here. As you can see, here device boot up occurs only occasionally. The device remains in low power state and is woken up from suspend state when external trigger occurs. In this demonstration, RTC alarm from PMIC works as an external trigger. The latency is measured between the device wake up interrupt and first frame dump in DDR. The device then waits for the first frame to arrive in DDR and measures the latency between capturing the frame and device wake up interrupt. After measuring latency, the device returns to the active state where it remains ready for the further action. The process then loops back to the camera reconfigure step, repeating the sequence of actions until the script stops externally. This loop allows the device to continuously monitor the camera, measure latency, and conserve power during inactive periods, ensuring efficient operation. To understand this better, here's a short demo showcasing the use case. As you can see, the device is previewing the camera feed on the display. The script sends device to suspend state. RTC wake alarm is set to 10 seconds. So after 10 seconds of sleep, the device wakes up and resumes previewing the camera feed. Once the RTC wake alarm triggers, the device wakes up from suspend and continues previewing the camera feed. We measured the latency using two approaches. In the first approach, the K-object timers from kernel are used to measure latency, while in the second approach, a GPIO toggle method is used. The image indicates that the first approach has an average latency of around 385 milliseconds, whereas the GPIO toggle approach measured latency around 360 milliseconds. Depending on different use cases, we measured average latency across three scenarios, which are recording the camera stream to internal storage, recording it to external storage, and previewing the camera stream on the display. Here are the latency results. This concludes our demonstration of the trigger-based vision system and its reliable real-time performance.